Hello everyone, welcome to the video for chapter 4.1. In this video, we're going to get an introduction to probability. We can say that probability is the chance of some event occurring. I'll tell you a little bit more about what I mean by the word event in just a little bit, but I think most of us, if I asked you what probability meant, you would say something like the chance of something happening, the likelihood of something happening, and you're right, that's really what probability is all about. Now, in this course, we will talk about probability primarily in terms of what's known as a probability experiment. A probability experiment is a chance process that leads to a well-defined result. Now, what I mean by a chance process is that whenever we do this experiment, there's a chance that we get this outcome, there's a chance that we get that outcome, and we really don't know which outcome we'll end up with until we actually do the experiment. For example, we could flip a coin. There's a chance it'll land on heads, there's a chance that it'll land on tails. We really don't know which way it's going to turn out till we actually flip the coin and observe the result. And if we flip that coin today and get one result, we can come back tomorrow, flip the coin, and get a completely different result. Or if you and I flip two coins at the same times, we might get the same results, we might get different results. That's what a probability experiment is. It's different than a scientific experiment, which would have repeatable results. An example of a scientific experiment would be to take a pot of water, bring it to a boil, and measure the temperature. If you do that, you'll get 212 degrees Fahrenheit. If you come back tomorrow and do the same experiment, you'll get the same result, 212 degrees Fahrenheit. If both you and I boil pots of water and measure the temperatures, we'll both get 212 degrees Fahrenheit. That's a scientific experiment with repeatable results. Probability experiments don't work that way. Now, the outcome or the result of our experiment is something that we'll call an outcome. So that's just another name that means the result of the experiment. That's the word that's typically used. Now, the sample space is an important concept when you have a probability experiment. The sample space is going to be the set of all possible outcomes in the experiment. So let's take a look at a couple of probability experiments here and identify their sample spaces. Let's say we toss one coin or flip one coin. The sample space would be heads or tails. Those are the only two possibilities when you flip one coin. Now, if you flip two coins, now you can get some different combinations of heads and tails. Both coins could be heads. The first one could be heads, the second one tails, or the first one tails and the second one heads, or they could both be tails. So you have four possible outcomes there. Now, if you think that the heads, tails, and the tails, heads might be the same because you've got one of each, well, that's not really the way you want to think about it. Think of having a penny and a nickel. If the penny were heads and the tails and the nickel were tails, that's a completely different picture than if the penny were tails and the nickel were heads. Since those are two completely different pictures, you got to think of them as two completely different outcomes. Now, they do have something in common, one of each, but they are distinct outcomes. If you roll a die, okay, if you have more than one of these, you would call them dice, but when you just have one, you call it a die. If you roll a die, you can get the numbers 1 through 6. So just making a list, 1, 2, 3, 4, 5, 6 would be the sample space. Now you can do multi-part experiments where you do something like flip a coin and roll a die. In that case, your sample space is going to be something like this. You could get heads on the coin, and any number 1, 2, 3, 4, 5, or 6 on the die, or you could get tails on the coin and any of the numbers 1, 2, 3, 4, 5, or 6 on the die. So there's 12 outcomes in that sample space. Now, what I want you to notice is that number 12 is not a coincidence. Okay, when you flip a coin, there's 2 possible outcomes. When you roll a die, there's 6 possible outcomes. If you multiply 2 times 6, you get 12. This is something known as the fundamental counting rule. When you have a multi-part experiment, if you want to know the total number of outcomes in your sample space, just multiply the number of outcomes for each part of the experiment. Now, something that can help us to get the sample space in a multi-part experiment is called a tree diagram. What you do in a tree diagram is you think of the first part of the experiment, which in this case is flipping a coin, and you ask yourself what could happen there. Well, that could be heads or tails. So you draw 2 branches here, one heads, one tails. And then what you do is you say, okay, let's assume that we get heads on the coin flip. what could happen on the die? Well, you could get any of the numbers 1, 2, 3, 4, 5, or 6. So notice I have the 6 branches coming off the heads with the numbers 1, 2, 3, 4, 5, and 6. If I flip the coin and get tails, and then go ahead and roll the die, I could also get the numbers 1, 2, 3, 4, 5, or 6. So I got 6 branches coming off of the tails there. And then to get your sample space, what you would do is you would start at the beginning of your tree and just work your way out to each of the endpoints and collect what you come across along the way. So heads 1, or you could have heads 2, heads 3, heads 4, so on. Tails 1, tails 2, tails 3, tails 4, all the way down to the last one, tails 6. So in a multi-part experiment, a tree diagram can help you identify the sample space. Okay, so earlier I told you that probability is the chance of some event occurring. Now, what exactly is an event? Well, an event is going to be a set of one or more outcomes in the sample space that we're interested in. These are the things that would make us happy if we see them come up as a result. The complement of the event is going to be the set of outcomes in the sample space that are not in the event. They're in the sample space, but they're not in the event. In other words, they could happen, but we're really not interested in these things happening, or we're really not looking for these things to happen. If our event is designated by the letter E, sometimes the complement of the event will be designated with an E prime. Okay, it's like a little apostrophe there, but we would call it prime. Sometimes you would see like E bar as well, like a bar above the E. Now there's a couple of rules associated with probabilities. First of all, probability is always going to be a number between 0 and 1. Okay, so the probability of any event is always a number between 0 and 1. It might be 0, it might be 1, it might be any number in between. But probability will never be negative, it'll never be greater than 1. Now that probability measures the chance that this event will occur. So you can think of that 0 to 1 as a spectrum. If the probability of the event is 0, that means it's impossible for the event to happen, and it never will. At the other end of the spectrum, a probability of 1 means that an event is certain to occur. It's guaranteed. It's going to happen every time. Now, numbers that are close to 0 mean that the event will be unlikely to happen. Numbers that are close to 1 mean that the event is likely to happen. It may or may not, but when the number is close to 0, that means chances are that it won't, even though it could. And whenever the probability is close to 1, well, the event may or may not happen, but it's likely to happen. If the probability is 0.5 or 1/2, then there's an equal chance of happening and not happening. So sometimes you hear a 50-50 chance. That's what we're talking about. 50% is another way of saying 1/2 or 0.5. Now, it's also true that the probability of an event plus the probability of its complement has to equal 1, which if you want to rearrange that equation, you could say that the probability of an event is 1 minus the probability of that event's complement. So for example, if the probability of winning a raffle is 0.1, the probability of not winning, which is the complement to that event, either you win or you don't, so the probability of not winning would be 1 minus the probability of winning, which is 1 minus 0.1, which would be 0.9. Okay, now how do we determine the probability of an event? Well, there's two different ways that we can determine the probability of an event. One way is known as classical probability. In classical probability, all of the outcomes in the sample space have to have the same chance of occurring. Okay, so we have to say here that all the outcomes in the sample space are equally likely to occur. If that's the case, then you can determine the probability of an event using what is known as classical probability, sometimes also called theoretical probability. If you're doing classical probability analysis, the probability of your event can be found just by counting how many outcomes are in the event and dividing that by the number of outcomes in the sample space. So for example, let's think of rolling a die. If I said, what's the probability of getting the number 3? Okay, well, let's think of the sample space here for the experiment where we're rolling a die. So the sample space, if you remember, is the numbers 1, 2, 3, 4, 5, and 6. If I say, what's the probability that we get the number 3, then you would say, okay, well, 3 is one of the outcomes in the sample space, and there are 6 outcomes altogether, so 1 out of 6. If I said, what's the probability of getting a number less than 5, I would say, well, that could be 1, 2, 3, or 4. So there's 4 numbers that are less than 5, 4 numbers in the event, divided by the 6 outcomes in the sample space. If I said, what's the probability of getting an odd number? You would say 1, 3, 5. That's 3 numbers out of 6. If I said, what's the probability of getting a number greater than 10? Well, there are no numbers greater than 10. So you have 0 outcomes in the event divided by 6 in the sample space. So that would be 0. That's impossible. It'll never happen. If I said, what's the probability of getting a number less than 10? Then all 6 of these numbers are less than 10. So 6 outcomes in the event divided by 6 outcomes in the sample space, that's 1. This event is guaranteed to occur. No matter what you roll, it's going to be a number less than 10. Okay, so we can do classical probability analysis here on this experiment because when you roll a die, you have the same chance of getting any one of these numbers. Okay, as long as the die is fair and balanced, and not weighted in some kind of way so that one side is more likely or less likely to show up than the others, you can do classical probability analysis. Another experiment where you can do classical probability analysis is when you draw a card from a deck. Now, you might not be familiar with a deck of cards, so let me explain. A deck of cards consists of 52 cards, and each card has 2 items on it. One is a value, and the other is a picture. The picture could be a heart, a diamond, a spade, or a club. The value could be any number 1 through 10. 1 is typically referred to as ace. And then there are 3 cards that have the picture of people's faces on them. Those are known as the jack, the queen, and the king. So you've got 52 cards. Each card will have one of these pictures, sometimes called the suit, and a value associated with it. The hearts and diamonds are drawn in red, and the spades and clubs are drawn in black. So if we were to take a deck of cards, shuffle them all up, and pick one out, we would have the same chance of picking any one of these cards, so we can do classical probability analysis. So what's the chance that we pick the 9 of clubs? Well, that would be the card that has the 9 and the club on it. That's one of the cards out of the 52 in the deck. So 1 out of 52. What's the probability that we pick a card with a heart on it? Well, any of these cards up here in the top row have a heart on them. There's 13 of them out of the 52 cards in the deck. So we would say 13 out of 52, which if you wanted to reduce, you could reduce to 1 over 4. The probability of getting the number 7. Well, there's 4 cards here that have the number 7 on them. So we would say 4 out of 52, which again, we could reduce to 1 over 13. You can convert that probability to a decimal, express it as a percentage. So fraction, decimal, percentage, any of those are valid ways to express your probabilities. Okay, let's do one more example here. Let's say we have 2 spinners. Okay, so by spinners, what I mean is we have these little circles with these arrows that you could spin the arrow and see what color your arrow points to. The first spinner could be red, white, or blue. The second spinner could be red, white, blue, or green. Now we can ask questions like, what's the probability that you get both spinners to land on red? Well, before we can answer that question, we probably need to identify the sample space here. It's a 2-part experiment because there's 2 spinners, so I'm going to use a tree diagram. The first spinner could be red, white, or blue, so I've got 3 branches there for the first spinner. And then no matter what color I get on the first spinner, I could always get red, white, blue, or green on the second. So if I get red on the first spinner, I could get red, white, blue, or green on the second spinner. If I get white on the first one, I could get red, white, blue, or green on the second. And if I get blue on the first, I could get red, white, blue, or green on the second. So I trace the tree from the beginning to end like I showed you how to do before, and I get my 12 outcomes. Okay, 12 here because we had 3 options on the first spinner times 4 on the second. Now, if I want to know whether or not I can do classical probability analysis here, I have to ask myself, do I have the same chance of getting any of these outcomes as the others? And the answer is yes, because these wheels are divided up in such a way that each color has an equal amount of area. Okay, if that wasn't the case, if one color had more area and other colors had less area, then we wouldn't really be able to do the classical probability analysis here. Okay, so if we want the probability of getting 2 red, notice that's one outcome out of the 12 in the sample space. If we say, what's the probability that we get both spinners to be on the same color? Well, that could be red, red, white, white, or blue, blue. So that's 3 out of 12, which you could reduce to 1/4, or convert to a decimal 0.25, or make a percentage 25%. If we want 1 white and 1 blue, okay, it doesn't really matter what order, so 1 white and 1 blue, we could get white, blue, or we could get blue, white. So there's 2 outcomes out of 12. Okay, that's classical probability analysis. That's how we can determine probabilities in a theoretical sense. There's another way that we can determine probabilities. It's called empirical probability. Empirical means observed. So sometimes this is called observed probability. And empirical probability is based on the results that you observe when you do the experiment many times. Now, you can use empirical probability analysis anytime. Okay, there's no restriction that the outcomes in the sample space have to have the same chance of occurring like it was for classical probability. Now, what you do in an empirical probability analysis is you do the experiment many times. You do the experiment many times, you keep track of all your results, and after you've done the experiment many times, you're going to look at your list of results and count how many times your event showed up, and then divide that by the total number of times you did the experiment. So for example, let's say that we wanted to take a random person. Let's imagine we're on campus at school, and we just take a random person from the hallway and we say, what mode of transportation did you use to come to school today? Maybe we want to know the probability that they took a bus to school. Well, we can't really do classical probability analysis here because there's probably a greater chance that somebody used one mode of transportation and a lesser chance that they use some other mode of transportation. So we're going to have to do empirical probability analysis here. And so to do empirical probability analysis, we'll have to ask many people what mode of transportation they used to come to school today. So let's say we surveyed 85 people and we found out 57 came by car, 21 by bus, 4 by walking, and 3 by bicycle. You can see that some events have higher chances of occurring and some have less. That's why we can't do classical probability analysis here. Now, if we want to know the probability that somebody came on a bus, we would just say, how many times did we get a responsive bus? That's 21. Out of how many times did we do the experiment altogether? That's 85. So 21 out of 85, which you can convert to the decimal 0.247 or the percentage 24.7%. Now, one last thing is known as the law of large numbers. Let's think about flipping a coin and asking about the probability that it lands on heads. If you want to find that probability in the classical way, you would write out the sample space, heads and tails, and then you would say heads is one of those outcomes out of the 2 possibilities, and you would say 1/2, okay, which would be 0.5 in decimal form. So if you wanted to, you could always convert this and say 0.5, or you could say that this is 0.500, depending on how many decimal places you want. Now, for an empirical analysis, let's say that we were to flip the coin 15 times, and let's say out of the 15 trials, 10 of them landed on heads and 5 of them landed on tails. Well, if that's the case, then the probability of getting heads with the empirical probability analysis would be 10 out of 15, which in decimal form would be 0.667. Notice those 2 probabilities really don't agree very much. Okay, well, this is where the law of large numbers comes into play. The law of large numbers says that as you do the experiment more and more times, the empirical probability should get closer to the classical probability. So 15 times is not very many times. If we were to do this experiment 1,500 times or 15,000 times, then we would expect the probability, the empirical probability of getting heads, to be a lot closer to 0.5. Now, if we were flipping this coin 15,000 times and we were still getting an empirical probability around 0.667, that would suggest to us that maybe this coin really isn't balanced. Maybe it's weighted in some kind of way so that it shows heads more often than tails. So you can use the law of large numbers to put a coin or a die or something like that to the test. Flip the coin many times, see if the probability of heads is close to 0.5. If it is, the coin's probably fair and balanced. If it's not, then you might suspect that the coin is unbalanced. Okay, that's an overview and an introduction to probability in chapter 4.1. We'll use some of these concepts as we go forward into chapter 5. I'll see you in that video a little bit later.